Let's consider three-dimensional curved coordinate systems. As an example, you have something like the Cartesian coordinates x, y, z going to r, theta, phi. Now, to develop the general theory, it's better not to commit yourself to particular coordinate systems. So I'll call the original coordinate system x1, x2, x3, and later on we'll put x, y, z. And the new coordinate system will be called q1, q2, q3. So x sub I is going to be a function of q1, q2, and q3. In this scheme, it's also useful to introduce a compressed notation for derivatives borrowed from general relativity, and that is 1, 1. So let's try to write one differential to see how this works. dx1 is going to be del x1 over del q1 dq1 plus del x2 over del q2 dq2 plus del x3 del x1 again del x1 over del q3 dq3. It's easy to get fooled by the rhythm of this thing. The only thing that changes is the thing with respect to which you differentiate, not the first thing. So 1 remains the same, and then these get summed up. So you can see the index structure working already. So I get x1, 1 dq1 plus x1, 2 dq2 plus x1, 3 dq3, which can also be written using the Einstein summation notation. I can write this as x1j dqj. So in general, I can write the other things also. dx2 is x2j dqj, and dx3 equals x3j dqj. So you can see how efficient it is to use the index notation. I wrote it in a matter of a minute. Once you have that, you can also talk about the coordinate transformations in the following manner. You can write these dx1, dx2, and dx3 in a column vector, and all these coefficients as elements of a matrix. So I'll write that as x11, x12, x13. As you're filling it, observe the structure. The column index always occurs second, and the row index always occurs in the first position. And then I get dq1, dq2, dq3. So one way to easily internalize this is to take the first coordinate transformation and differentiate it with respect to q1 and finish all the three functions x1, x2, and x3 and differentiate them all with respect to q1. Take the three functions, differentiate them all with respect to q2. So you go column wise. That's the trick. This quantity here is called a Jacobian matrix. It's just a name. It's also written as BIAN. And in terms of the Jacobian matrix, I can simply write this as dx vector is equal to j times dq vector. So that's a compressed way of writing that one. The determinant of the Jacobian matrix is a very important quantity, and it tells us a lot of useful things. So the determinant of J essentially gives us the volume element. So if we have the volume element dV in Cartesian coordinates, it's just dx1 wedge dx2 wedge dx3. And in the other coordinate system, it would be the determinant of Jacobian dq1 wedge dq2 wedge dq3. The wedges are strictly not necessary for three of them because it's basically the triple scalar product. Now, what I'm going to do here is write the arc length element ds. Next, ds is dxi hat plus dyj hat plus dzk hat. That's just the way you would write it for Cartesian. Now I'll substitute for dx, dy, and dx, dy, and dz. Well, except this will be called dx1, dx2, and dx3. So I'll substitute for them, and I'll end up getting x11 dq1, I won't write everything, x13 dq3 I hat plus x21 dq1 x23 dq3 plus j hat plus x31 dq1 plus x33 dq3 k hat. So I'm going to assemble these into a single vector known as aq1 dq1. So aq1 will have the first term of this, the first term of that, and the first term of that, because they have all dq1s with them. And aq2 times dq2 plus aq3 times dq3. These aq's are important objects. They're called the coordinate vectors of this coordinate transformation. So a times a subscript q comma l. The q just stands for the new coordinate system. Don't pay attention to that. L is the more important one. And that's equal to x1 l I hat plus x2 l j hat plus x3l k hat. These are called the coordinate vectors. Again, compressed resonance, you can write this as aqj dqj if you wish. There are some important coefficients which I'm going to define next, known as the Lamia coefficients. Please don't say lame. The Lamia coefficients are essentially the length of these coordinate vectors. How is the length of a vector defined? It's just a square root of the components squared. And then once you have that, I can write the AQLs as HLs times the unit vector in the direction of AQLs. So I'll write them as HL times EQL times DQL. I've changed the index from J to L. Okay, now that's it. That's a general theory. Now, general theory is all fine, but specific examples really bring the theory to life. So let's go to the polar coordinate system, the spherical polar coordinate system example I started out the video with. For those who need a refresher on that, here it is. It's got three coordinates. The x, y, z coordinate system is just that. And then you have a generic 3D vector. That's your r coordinate. It tells you how big that vector is directly. The theta coordinate is sometimes called the co-latitude because it's 90 degrees minus the traditional meaning of the latitude. Latitude is usually measured from the xy plane. This angle is called the azimuthal angle from the days of sailing, when sextants were used to measure your reckoning of the azimuth. So the spherical polar coordinate system is defined by the following systems of equations. x1 is r sine theta cosine phi. And I'll write S for sine and C for cosine to save writing time. x2 is r sine theta sine phi. And x3 is r cosine theta. So in this scheme, our q1, q2, and q3 essentially become r theta and phi. All right, we are now ready to write the Jacobian matrix J. Remember the shorthand. You take these things and differentiate first with respect to r and write the entire column. So I'll do that. That's sine theta cosine phi, that's sine theta sine phi, and that's cosine theta, because they're all linear functions of r. Then I differentiate with respect to theta. So I'm going to get r cosine theta cosine phi, r cosine theta sine phi, and negative r sine theta. Then with respect to phi, so I get negative r sine theta sine phi, r sine theta cosine phi, and this does not have a phi at all, so it gets a 0. The Jacobian determinant, normally I would have expanded from the first or the top row, but this time it's pretty obvious I should use the bottom row, so let me do that. That's a sign assignment for the determinants. So I get cosine theta times this minus that. That's r squared cosine theta sine theta cosine squared phi, and that's minus of a minus, so that's plus r squared sine theta cosine theta sine squared phi. And this second term is going to be minus of a minus, so again it gets plus r sine theta, and then this minus that, so that gives me r sine squared theta cosine squared phi plus, because of minus of a minus, r sine squared theta sine squared phi. That is going to simplify quite a bit, because cosine squared plus sine squared is 1, so that gives me r squared cosine squared theta sine theta plus this one, again r squared comes out, sine theta, and that's just cosine squared plus sine squared equals 1 again, so that's sine squared theta. Well, that's further sine squared theta plus cosine squared theta equals 1, so that's just r squared sine squared theta. That's a famous factor you get in coordinate transformation from Cartesian to polar. So writing x, y, z again, I get r squared sine squared theta dr d theta d phi. Now let's also calculate the Lamia coefficients in this example. They are pretty straightforward calculations, because all you've got to do is square and add the first column for h1 and so forth. So h1 is going to be the square root of sine squared theta cosine squared phi plus sine squared theta sine squared phi plus cosine squared theta. Once again, cosine squared plus sine squared is 1. That gives me sine squared plus cosine squared is again 1, so that whole thing is 1. h2 will be the square root of everything that occurs in the middle. So that's r squared cosine squared theta, middle column. And doesn't matter that there's a minus sign there, because it gets squared and it goes away. Here, if you look at this, they add up to 1, which means I get r squared cosine squared theta. But r squared cosine squared plus theta plus r squared sine squared theta is just r squared, which when you take it out of the square root becomes an r. And in the same way, h3 is r sine theta. So I can write the arc length element as the last thing I do. So ds is going to be following the protocol I laid out here. It's the unit, the Lamia coefficient times the unit vector in the direction times the element dq. So the Lamia coefficient h1 is 1, the unit vector in the direction of dq1 is r hat, and the actual differential is dr, plus Lamia first, unit vector next, differential third, r sine theta phi hat d phi. So in this way I found the arc length element 2 in the polar coordinate system. This procedure that I just outlined here can be applied to any coordinate system whatsoever, and there are numerous coordinate systems. It can be applied in any number of dimensions, and as you'll see in the next video, these Lamia coefficients are central to the definition of gradient, divergence, and curl in various coordinate systems. And so let's just summarize what's going on here, because lots have happened. You take the coordinate system that you start with, right? It's defining equations, form the Jacobian, and once you form the Jacobian, you then form the Lamia coefficients, and then go forward from there. So it's a pretty intricate several-step procedure.